Hi, I am Harshit, and along with Tianwei, Yufei and Tejas, we'll be presenting a work called f-IRL, Inverse Reinforcement Learning via State Marginal Matching. Let's start with some motivation. Why do we want to imitate? Atari provides a real reward function, but in real-life scenarios like autonomous driving, it is not obvious at all what the reward function should be. In general, designing reward requires striking a fine balance between different preferences to achieve the final objective, which can be difficult. Now that we have seen the importance of imitation, where do these expert demonstrations come from? The slide shows some examples where expert demonstrations were obtained from human skills, animal motion, or kinesthetic demonstrations. We can generally classify the demonstrations in three forms. Trajectories, which are an ordered in time collection of state action pairs. State action pairs, where we have the correct action for each state, and state marginals, which don't require actions to be known. Our method can learn either from observations or using state density. Specifying a state marginal can be easier than giving expert trajectories for several tasks. For example, in complex robots like the ant, it might be difficult to obtain expert trajectories. For uniform exploration, we can specify a uniform density over the entire state space as the state marginal. We can also encode safety trivially by setting the density of unsafe states in the environment to be 0. In contrast to previous methods, our method f-IRL works in the state marginal space to minimize general f divergences while requiring the policy as well as the reward function.
f-IRL learns a reward function to match the expert state density. Our objective function is a general f divergence between the expert state distribution ρe and the state distribution induced by our agent, rho theta. For example, we can optimize for the forward scale and the reverse scale divergence to learn mode covering and mode seeking policies respectively. We derive the analytical gradient of our objective with respect to the reward parameters. The gradient formula is the covariance between the reward gradient and the sum of H transform of density ratios. Intuitively, the gradient tells to increase the reward for the trajectories that have a higher sum of density ratios. This slide explains our overall algorithm. We first run max and RL to sample trajectories for the current reward function r theta. Then we estimate the agent state density and plug it into our gradient equation. And then we use gradient descent to optimize the reward parameters.
We now present the experiment. In the first experiment, we investigate whether f-IRL can successfully match a specified expert density. The task is to move the fingertip of the virtual robot. We consider the expert density to be a Gaussian distribution centered at the goal region. We say that if f-IRL matches expert density better, it should be no KL divergence in state marginal compared with prior method. We now show how the reward learned by f-IRL evolves during training. The left plot shows the Gaussian expert state marginal that f-IRL tries to match, and in the right video, we show how the reward and the corresponding agent trajectories evolve. As can be seen, f-IRL gradually adapts the reward to focus on the high-density region, and the agent trajectories obtained using the learned reward also goes to the high-density expert region, showing that f-IRL can successfully learn reward to match the expert density. We now test f-IRL on standard Mojoko imitation learning benchmarks. We compare f-IRL with several parameters on 4 environments with only one expert trajectory. We see that in all environments, f-IRL is more sample efficient than prior imitation learning and inverse RL methods in terms of environment interaction steps. We also see that f-IRL can recover a policy whose performance is very close to the expert. We now do a comparison of the learned policies on the worker environment. We see that the policy learned by f-IRL works much faster than the baseline and achieves the highest return.
Besides learning policies from state marginal matching, f-IRL also learns rewards. Here we show two typical examples of their utilities. The first example is to help exploration downstream tasks. Suppose we have a continuous 2D grid reward for goal reaching task. The agent starts from the bottom left corner and is expected to reach the goal at the top right corner with the highest task reward. However, the environment also has task reward on the other two corners to distract the agent. To solve this task, we need to do reward shaping, which encourages the agent to explore. We call the extra reward in the shaping term as prior reward for exploration. Instead of manually design, we can use inverse IO to learn it. f-IRL naturally learns the prior reward by matching the uniform state density as exploration task. The left figure shows the learned reward by matching the uniform state density from different imitation learning methods. It's clear that f-IRL learns a better reward function than the two baselines. The furthest point should have a higher reward to match density. Then the right figure shows the final performance of the SS agent with shaped reward function. We can see that f-IRL together with maximum can solve the hard-to-explore tasks with most of hyperparameter combinations, while fmax and GALE often fail. Next, we show another utility of learned rewards. Consider we have expert trajectories from the healthy ant task. Now we change the ant dynamics to disable the front legs of ant, but the ground truth reward still holds. f-IRL is shown to learn the stationary reward across dynamics, and we verify it by this experiment. The learned reward from the healthy ant trajectories can be transferred to learning a good policy in the disabled ant.
In summary, f-IRL learns a reward function to match expert state marginals in any f divergence by gradient descent. f-IRL is more sample efficient than baselines. The learned rewards are useful for downstream tasks such as hard exploration and dynamics transfer.